Hi, my name is Arlene Reyes and I am a robotics engineering student at the Universidad de Guadalajara in Mexico. In this presentation, I will talk about the project I developed during my summer research at the Reyes program at Carnegie Mellon University. The title of my project is Hammer, a skin-adhered haptic device with multimodal feedback for enhanced rehabilitation. In this work was conducted under the mentorship of Dr. Melisa Orta Martinez, Dr. Eni Alilaj, and PhD student Iki Balam Heredia Marin. Knee osteoarthritis is a degenerative disease that causes pain, stiffness, and difficulty in movement. A key factor in rehabilitation is correcting the foot progression angle, since improper foot correction that increase joint stress and delay recovery. Traditional solutions require expensive laboratory setups. Therefore, there is a need for a portable, real-time feedback system to support gait correction outside of the lab. These are the main contributions of my project. I developed a wearable haptic device with real-time visual and haptic feedback, implemented 2 usage modes, created a custom calibration progress, and enabled wireless communication via Wi-Fi. This is the physical design of my hammer device. It uses adhesive electrodes to attach to the skin and Velcro tape for secure placement. Altogether, hardware components are enclosed in a 3D printed casing that I designed. System architecture. This diagram shows how all the system components are connected. The switch is used to power the device on or off. The bottom triggers the calibration progress for the IMU, which measures the foot angle and sends data to the SP32 through the multiplexer connector via STIMA QT cables. The SP32 processes the data and decides whether to activate the vibration actuators. In manual mode, it receives commands from a Python server over Wi-Fi. This dashed line indicates that the system can also operate in automatic mode without internet or server connection in a completely offline configuration. Visual feedback. This is the visual feedback provided to the system. The LED changes color depending on the current mode and the foot's orientation. This allows the user to understand in real time whether their gait is within the correct range or required adjustment. In automatic mode, the device uses the IMU to detect foot orientation. If the angle exceeds ±10 degrees, it vibrates the corresponding side and upplays the LED color, pink for left deviation, blue for right, and green when aligned. This mode operates fully offline and does not require any external system. In manual mode, the device connects to a Python server over Wi-Fi. Through this interface, the physician sends commands to trigger vibrations, switch modes, or activate calibration. The system also sends IMU data back to the Python server in real time for visualization and logging. To improve accuracy, a calibration routine is implemented at startup. The user captures 7 known foot positions using the bottom. After collecting all 7 samples, the foot is returned to the neutral positions, 0 degrees, and the bottom is pressed one more time. A linear regression is applied and the LED turns green to indicate that the device is calibrated and ready. From this point on, it goes in automatic mode. In the first test, users were asked to identify whether the vibration was on the left, right, or both sides. Accuracy was high, especially when only one actuator was triggered. There was slightly more confusion when both actuators were used, but performance remained strong overall. The second test evaluated participants' ability to distinguish between 5 unique vibration patterns. These included a single short pulse, double pulse, triple tap, ding-dong, and ramp up-down. Users were able to reliably distinguish the different patterns with minimal confusion. The Hammer device improves upon existing tools by offering portable, real-time haptic and visual feedback outside of the lab settings. Users successfully distinguish both the site and type of vibration. Future work includes clinical validation with osteoarthritic patients, integration of pressure sensing insoles to analyze foot pressure distribution, and ergonomic improvements for long-term use. Special thanks to Carnegie Mellon University, the Reyes program, Rachel Borsin, John Dolan, and Juan Alvarez for their support. I also thank to Universidad de Guadalajara, CUSEI, and Deans Marco Perez and Carla Planter for making this experience possible. I'm deeply grateful to my mentors, Dr. Melisa Orta Martinez, Dr. Eni Alilag, and PhD student Iki Balam Heredia Marin, and to the entire ShredLab team. And thank you for watching.